Hello everyone, I'm a student at the University of Chinese Academy of Sciences. The title of my paper is Generic Sensitivity, Customizing Context-Sensitive Pointer Analysis for Generics. For the first time, we propose a new context customization scheme for generics. Pointer analysis statically computes the abstract locations of pointer variables in a program. Typically, abstract locations are represented as allocation sites. Pointer analysis provides a foundation for a variety of applications, and several famous analysis and compilation frameworks implemented pointer analysis. There are rich papers optimizing the efficiency and precision of pointer analysis. They usually focus on field sensitivity, flow sensitivity, context sensitivity, and path sensitivity. One of the key mechanisms to improve precision is context sensitivity. In context-sensitive analysis, both pointer variable and abstract location are qualified with context, effectively distinguishing their different dynamic instances. Traditionally, the context of pointer variable is called context, and the context of abstract location is called heap context. There are three mainstream variants of context sensitivity: call-site sensitivity, object sensitivity, and type sensitivity. In general, a context is represented by a sequence of key context elements. For call-site sensitivity, the context elements are call sites, such as line 3 is the context of function foo in our example. For object sensitivity, the context elements are allocation sites of receiver objects, such as allocation site O in our example. For type sensitivity, the context elements are types of receiver objects, such as type A in our example. Among the above three variants, object sensitivity and type sensitivity are considered to be more suitable in analyzing object-oriented programs. As the depth of context increasing, the results will be more precise. On the contrary, the time and memory overhead will grow exponentially. In practice, the depth of context is often set to less than 2 for scalability. To better balance precision and efficiency, we propose a new context customization scheme for generics. Generics is a style of computer programming. It has been widely adopted and used in modern programming languages. Comparing ANTLER 4 to its earlier version ANTLER, the number of generic class instantiated sites grew a lot in ANTLER 4. Next, we will illustrate how to customize context-sensitive pointer analysis for generics by using an example. In the main method, there are two hashmap objects, O1 and O2. Object OA is created and passed into the method ID as parameter at line 3. Then this method returns back OA. Similarly, object OB is created and passed into ID at line 6, then retrieved back. As a result, the two cast operations will never fail. The simplified code snippet of hashmap is given in line 9 to 19. The ID method creates a node object and invokes its ID2 method, which just returns the formal parameter. In one object-sensitive analysis, the receiver object of the call to ID method at line 3 and line 6 are O1 and O2 respectively. Hence, the call to ID methods at different call sites can be distinguished using context O1 and O2. So we can distinguish the point2 set of variable v under the two contexts. In ID2 method of node, O3 is only one receiver object with one object analysis, so the point2 set of variable n will be confused. As a result, call to ID method will return a variable pointing to both OA and OB, leading to custom few false alarms at line 4 and line 7. The example can only be precisely analyzed when the context depth is set to more than 1. With two objective sensitive analysis, ID2 method is analyzed twice with two distinct contexts, O1, O3, and O2, O3. Thus, we can precisely compute the points 2 set of N. Finally, we can correctly avoid false custom-made field alarms. The real implementation of HashMap is much more complicated and may require a deeper context. Many modern programs can be precisely analyzed only with a very deep context. If we customize context-sensitive pointer analysis for generics, we can get precise results efficiently. At line 2 and line 5, we instantiate the generic class HashMap with actual types, so we can get two generic mappings, from V to O1 and V to O2. Then we can use these generic mappings as the context of method ID at line 3 and line 6 respectively. Then we can calculate precise points 2 set of the parameter V of method ID under different contexts. At line 11, we instantiate the generic class node with actual type parameter V, which is the formal type parameter of HashMap. However, according to the different contexts of method ID, we can detect the mappings from N to O1 and N to O2 respectively. So we can distinguish the method's ID2 according to different context mapping. Then we can get precise points to set of variable N. Finally, we can correctly analyze that variable A points to OA and variable B points to OB, avoiding false custom-made field alarms. Type-sensitive analysis is less precise than object-sensitive analysis. Hence, one-type analysis cannot distinguish the points to set of A and B, yielding same false alarms. Moreover, the standard two-type analysis cannot distinguish the context in analyzing the ID2 method of node either, since both O1 and O2 have type HashMap. We can also customize type sensitivity with generic and avoid false custom-made field alarms. If we handle both generic class and generic method, the situation will be more complicated. To implement generic sensitivity, we extend traditional context to a tuple, where G records all instantiation sites or actual types for formal type parameters. This slide lists 5 rules for analyzing the 5 can statements: new, assign, load, store, and call. For statements new and call, we use update and append functions to update generic mapping. Other 3 rules are same as standard K-object sensitive analysis. The details of rules are in our paper. Similar with object sensitivity, we use update and append functions to update generic mapping in type-sensitive analysis. We evaluate generic sensitive pointer analysis by using 18 popular benchmarks. Following previous papers, we measure the precision of context-sensitive analysis using the 4 metrics. For a benchmark chart, generic context customization enables one object-sensitive analysis to achieve similar precision with 2 object-sensitive analysis. Meantime, generic context customization can speed up 62 times. Comparing to one object sensitivity, generic context customization can achieve much better precision. At the same time, it can still speed up 7 times. 2 object sensitivity timeouts for 5 benchmarks. 1 object sensitivity with generic customization can analyze all of them. For other benchmarks, generic customization can speed up 12.6 times on average. If we only use generic sensitivity, we can achieve noticeably more precise results than one object sensitivity for all metrics across all benchmarks. One object sensitivity with generic customization can achieve slightly better precision than 2 object sensitivity. To represent the trade-off between precision and performance, we plot precision in each method's metric against the analysis time over benchmark antler. Lower numbers are better on both axes. Hence, analyses in the bottom left corner are superior in both precision and performance. The three variants of generic sensitivity achieve overall best trade-offs between precision and performance. For other benchmarks, we can get similar results. In a word, we present generic sensitivity and implement its variants in VALA. We evaluate a large set of applications and find that generic context customization can achieve overall better precision with a significant speedup, 12.6 times on average and up to 62 times. Thanks for listening.